something, I think, interesting for that. This morning I have been talking about things that are happening, processes that are happening in compressors. Yesterday it was more about bigger picture, ammonia and similar stuff. Right now, I'd like to talk something about the heat transfer in especially in heat exchangers in condensers. And as you see here, I'm trying to say that there is something actual, or svarno. That means that it is a little bit different than what most of us think about the process. And first of all, just a second. Okay, now we are going here. So I'll start with relatively conventional slides, talking about typical design conditions for the condensers. That would be on the left side is how the process looks like for 410A or for CO2. For CO2, we very often in heating or cooling go into transcritical cycle. And when we look into conventional fluids that are operating always in subcritical mode, most of the heat exchange in a condenser is in a two-phase zone. Nevertheless, in order to improve efficiency, very often even CO2 system operate in subcritical mode. When is that? Typically when the ambient temperature is below 25, around 25 degrees C and below. CO2 systems operate in a normal subcritical, following normal subcritical cycle. We are not in transcritical, so heat rejection is not in supercritical region. This portion here of this superheating is becoming extremely important. We typically think about the process in the condenser divided into three zones: superheating zone, two-phase, and subcooling zone. And that is how most of the models think about and how they are made. I don't know how many of you have designed or modeled condenser. I don't see too many hands, but I will imagine that you are just shy and you don't want to say that you did. Because whenever you want to make a model of a condenser, you divide that condenser into three zones. That's the way how it is done today. 99.9% of people will do that way. In other words, in this cycle, in this here heat rejection line, the inlet is single phase, some single phase correlation used for that, Gnielinski or Ditus-Bolter. And then when you go here in the two phase, people typically use Cavallini or Tommy or Shaw or whatever correlation. So divide these zone, and then in subcooling it is again single phase heat transfer. Again, depending on whether there is turbulent or laminar, which correlation you're going to use. That's how it's done. Nevertheless, the process doesn't look like that. And those of you who have made the calculation, you have seen tons of problems because of discrepancy in the heat transfer, because if you follow this type of approach, your heat transfer and the inlet of two zones suddenly jump from very low value to very high value, then it goes down and then it drops here to a lower value, which is not physical. First of all, it is impossible to have this type of difference in heat transfer coefficient suddenly for no reason. It is not a critical point. So this is a problem of our ways how we think and the way how we calculate. Now let me say something about how we think. Very often, and I will say it, hoping that I am hitting maybe some understanding. Condensation never happens at the tube. Evaporation in evaporator always happens between the fluid and the tube. Condensation happens, vapor condenses not on the tube, inner tube of the condenser. Condensation happens at the liquid film. Condensation happens between the vapor phase and the liquid phase, because liquid film is always covering inner part of the tube. That is sometimes, very often, misconception that many people think about. Condensation does not happen on the tube. I will repeat that. And I will show you videos and measurements that will help us in understanding that. And that is that novelty that I think that I'm bringing with this presentation. So, how it looks like really in the tube. So I'm here showing from the right to the left the process in the condenser. Zone 1 and Zone 2. So this, what we typically call this superheating region, it has really first real single phase superheated vapor, and then we have zone where the film starts to form. And I will show you measurements which will show dramatic increase in heat transfer coefficient when film forms, and we are in this superheating region, which is unexpected, maybe, for many. And then we are entering into two-phase region here, and for some reason, this heat transfer coefficient jumps, and for wrong reason. Okay, these are the measurements. Measurements here are done for CO2 at 50 bars. That means we are below critical point. And this here you see temperature of the surface of the tube, which is this green, and these two are inlet and outlet temperatures in some small section of 15 centimeters in that zone. When we are in this here is a heat transfer coefficient that we have measured, determined in experiments. So what can you see? In this so-called superheating zone, the inlet temperature is much higher than the outlet temperature from, let's say, 15 centimeters long test section. That temperature difference means that we are in the single phase. And the temperature of tube is relatively high. The moment when, the temperature of the tube becomes equal to the saturation temperature, which is shown here, we have opportunity for liquid film to be formed. The center of the tube, this is a cross-section of the tube, is still very superheated, but we can have liquid film inside the tube because the tube is at saturation temperature. It used to be at a higher temperature, but when it reaches that saturation temperature, we can have the film here. And the heat transfer coefficient from this, let's say, this would be predicted by Gnielinski, and this would be predicted by Cavallini. Suddenly, actual heat transfer coefficient becomes much higher. We are not talking about 5%. We are not talking about 10%. We are talking about 5 times higher. 5 times higher. Why nobody looks at that way? The answer is relatively simple. In the normal condensers, let's say ammonia condensers, whatever, this zone of this superheating here is relatively, excuse me, this zone is relatively small and not that important. But I have shown to you that, for instance, if I go back, in the modern, either new fluids like CO2, or whenever you go close to critical point, suddenly, look at this. Heat transfer in this superheating zone, whatever you call it, is 5 times, 3 times greater than in two-phase. When you look into ammonia, you have a huge latent heat of vaporization. So this superheating is relatively small, percentage-wise, and then it doesn't affect too much calculation, modeling of your condenser. Now, when you come to a situation like with CO2 or some other fluids that operate close to critical point, and we are seeing that more and more, like in high temperature heat pump that Mr. Gone was talking this, well, this becomes more and more important. Okay, let me now then give you some more details. So why did we struggle? Really what is happening is, the problem is that in this zone, we assume thermal equilibrium between a vapor and or uniform temperature, if you will, or thermal equilibrium in that zone between the vapor and the tube. It is not. We have in this tube inside here, we have, or if I go back, in the cross section, this temperature in the center is significantly higher than the temperature next to the wall. This is really what changes everything. Okay, so this is another measurement. And what that means, okay, those of you who are familiar with the two-phase flow regimes, maps, they know this map. There are many two-phase flow regime maps. Baker's maps for two-flow that try to talk about the vapor and liquid mass fluxes is one. And this is the most common. These flow regime maps were typically made from a diabatic point of view, like Taylor and Duckler's at the beginning. And then in Tommy's group, Kajal and Tommy and Cavallini were working on for condensation and for evaporation, Catan and others. And this is a typical flow regime map that you can find in Faude E-Atlas. And this here is mass flux as a function of quality. And now the process in the tube, mass flux is always constant. And then we can see either stratified flow regime when the mass fluxes are low, or stratified wavy. And then we have intermittent plug slug. Then it goes to annular, and sometimes at very high mass fluxes, the flow regime map predicts mist flow. I will show you, and I'm telling you now, this is absolutely impossible. It is impossible because there is not, number one, it is impossible to have a mist flow in condensation, because condensation always has to start at the wall. Because first, walls are the coldest part of the condenser. Condensation has to start there. And I will first show you the photographs and then later videos. These videos and photographs are very interesting. They are very unique because, to my knowledge, I haven't seen too many, if any, diabatic flow maps and diabatic visualizations. People do that in adiabatic conditions. That means there is no heat transfer when people take video. These photographs and these videos are taken through one glass tube, inner glass tube, and the water in the annulus. So condensation happens in the inner tube, and there is an annulus of water that is there to provide cooling, and there are two glass tubes. So we are watching here through first glass tube, through water, through second glass tube, and we are looking now into the flow regime inside. So what you can see here is this line, vertical line here, is where quality, bulk quality is 1, and where bulk quality is 0. This here is entropy for 134, enthalpy, sorry, for 134A. That means in a dome, this is where the right-hand side of the dome would be, and this would be where left-hand side would be. These numbers here are bulk superheat or enthalpy here. And this here is just how much of liquid we have inside. So what you can see here, starting from right to the left in condensation, you would expect that somewhere here, suddenly two-phase condensation starts, And this here is empty of liquid, that only vapor is happening in this part. But it's not the case. Let me show you now the videos. Let me try to make it work first. Okay, now all of these videos are presented here simultaneously. What can you see here? In superheated zone, you see here some film, and especially that film is visible also here in entire condensation process, because this is two-phase with a superheat of 32, 23, 14, 6, and this is quality 1. In this quality 1, you shouldn't be able to see anything, and film should be starting only here. But you see over here film that is being formed inside of the tube. And at higher mass flux, the same situation, film is formed much before bulk enthalpy is 1. What that means, I still haven't quantified anything, what it means for the calculation of a condenser. And I will tell you at the end. But the point here is that the physics of this heat transfer and condensation is a little bit different than we are taught in schools, or what kind of expectations are. What is wrong with a two-phase flow method? It is impossible to have a mist flow because condensation have to start from film. And over here, this map is telling us that we could have immediately stratified flow and wavy flow. And where is the beginning of the film? Something is missing. This is a missing information. So how should that look like? And this is a new flow map, basically extended in diabatic condition. It is extended beyond bulk quality of 1. That means here we would, in thermal equilibrium, we would have here vapor only at the saturation temperature, and then it starts condensation. Now, as I said, condensation starts much earlier, and it goes as it's presented here through the entire heat exchanger. What that means is we would like to know what is a heat transfer coefficient and how much is liquid inside, which is determined by the void fraction. And a void fraction is really how much is vapor inside compared to the total volume. That means 1 minus void fraction is really how much liquid we have inside. And these, and I will go relatively quick through that because the essence is more in what I've just said. Current void fraction models are either based on slip ratio or Lockhart-Martinelli parameter or mass flux based that take effect of non-equilibrium or history of a flow. And what we have done is try to see which of these are good. And what you see here are actual measured film thicknesses in the tube using the same method that is, for those of you who have been here in the morning, I had presented the way to measure the film of liquid inside the tube from the outside using laser. So the same method we have used to measure the film of liquid as long as the flow regime is annular. So we know how much liquid is inside, which is very important to say something about the heat transfer coefficient. And this is for various mass fluxes, 50, 100, 150, 200. These are typical mass fluxes on the low end, and this is more on a usual end for the normal condensers. In microchannel condensers, we can see something going all the way to maybe 700, 800. So obviously, here we have measured and quantified that thickness of the film. What that means, this is a void fraction below 1 before. Earlier, these are homogeneous ZV and Smith models for the void fraction. These are our data from the previous picture. So what you see here, that void fractions here are very different than what correlations would give you. This is our prediction of the void fraction. That means how much liquid this in a void fraction that goes from 0 to 1, for those that are not familiar. This means, as a function here of quality or enthalpy, when the void fraction is 1, that means there is a vapor only. And between 1 and this line, this is how much of the volume is filled with liquid, and the rest below the line all the way to the 0 is how much of the volume is filled with vapor. So basically, with the measurements of thickness of the film in annular flow, we are able to experimentally check, and now theoretically we made a model for and validated with these experiments for void fraction inside, having in mind a real process in a condenser with condensation in so-called the de-superheating region. Here what is interesting, I'm showing you for the same condition, two fluids, 134A and 32, and I think we will have towards the end of the presentation something about 32, and you will see later a little bit more data. It is very interesting, and whoever had done any measurement with 32 has extremely good heat transfer characteristics, much better than, for instance, 134A. And one of the reasons is that it has a much higher latent heat, and thus the film here is much thinner than for, let's say, 134A. Ammonia would have even thinner film. Thickness of the film is resistance to the heat transfer. If you want a good heat transfer, you want thin film. So that is one of the explanations, and this is experimentally obtained value for the film thickness, and that is why, for instance, one of the reasons why 32 behaves that way as it does. Now, to go to heat transfer just a little bit and very quick, typically we have models that are gravity-driven in condensation, like Nusselt film theory, Chato, and others, shear-driven. But I like a much better flow regime-based, which has started really in our lab in 1998. Professor Chaka, who is over Chato, and his student Monty Dobson had been working on that for the first, and later a few others, Cavallini had adopted that, started working, John Tommy in Lausanne, in Switzerland, and Cavallini improved it, and now Srinivas Garimella with his student McDonald, they have started working, and I think we are here adding a little bit to that. And we have developed that new model, and I will give you just some of the elements of that approach, and that the blue is really our model compared to Tommy's model, Cavallini, and compared to experimental data that you see here. Basically, I will skip this. This is maybe not that important. One of the, or maybe here to use, I don't know whether now I'm going too much into details, but those of you who understand heat transfer, and I believe there are most of you like that, you are here probably asking yourself, what is physically happening that heat transfer coefficient here jumps so high? You have seen now, and I believe you trust me, you have seen that film starts here. And from visualization, there is nothing that indicates that heat transfer here is so high. That is one of the flaws of our measurements, of our, modeling. And that is, and I will show you that that is because of the way how we treat the temperature of the fluid inside. Because engineering approach is very logical. And I am still saying it should stay that way, but our understanding should be different and the modeling should be improved. It is that we know what is the bulk value of the enthalpy inside of the tube. That means we are assuming in this zone, so-called the de-superheating zone, we assume the temperature is the average or bulk temperature of fluid, and when we determine heat transfer coefficient, or when we use the heat transfer coefficient for calculation, we have a temperature difference which is bulk temperature difference minus bulk temperature minus wall temperature. While here, in condensation, we immediately switch to saturation temperature because we believe that fluid is at saturation. And heat transfer coefficients look so much higher. But this is mathematically presented what I was trying to tell you. In conventional heat transfer coefficient, this is that bulk. We have capacity divided by bulk temperature minus wall temperature. This is that, and that could be divided here into this temperature difference into bulk minus saturation and saturation minus wall. If we think about this process more physically, the heat transfer occurs at the wall, and that means that this heat that is transferred is really transferred because of saturation temperature at the interface, no, not saturation, minus wall temperature. Then this heat transfer coefficients here would be way higher. And if you will, this is the conventional thinking, and this is what actually it is if you calculate the temperature of the fluid to be the film temperature. And then now suddenly we don't see any magic around quality of one, which our visualization and our measurements cannot support. It is not physical at all. So we have then made a model for that and returning that back to the conventional calculation. So now we will run this model in the following way. First, really this superheating when we have only single phase, and then here we have a film heat transfer coefficient, and here film again, and we will recalculate that to a bulk. So, asymptotically thinking, on the left side of this diagram, we have only vapor flow. On the right side, we have vapor flow. On the left side, we have liquid flow. Both of them can be described with some sort of equations for a single phase heat transfer, and you can take Vitus, Bolter, Jelinsky, whichever you want, or something which is more adjusted for laminar if there is any situation with for having laminar flow in the liquid, on the liquid side. While mechanicistic model that we are proposing is to go from this really vapor flow to a very thin film and to thicker film that could show here some effects of gravity and thickening towards the bottom. And then when we go from annular, fully annular flow to some kind of annular stratified flow and filling it up, and we will come here to the end of the process of condensation. So this is way more physical way of thinking about the process of condensation and calculating. And I will try to go faster because you can find that in the journals much more. Demonstration of this complete condensation is presented here, model of condensation. This is how vapor flow looks like, thin film, annular flow, and here we have some sort of stratified wavy, if you will, and then almost feel stratified with a very, very low velocity of a vapor here, and then liquid flow at the end. So these are this is the most important how this thin annular flow looks like. This is how stratified wavy flow looks like. This is how slowly, very lazy, the flow of liquid with Kelvin-Helmholtz instabilities it could just pass, turn that stratified wavy into intermittent flow regime. And this is how it looks like, just in one picture, how the model goes along this process of the heat transfer coefficient. The model is pretty good, within 15%, and I will very quickly go through this now. These are validation for different refrigerants, for R32, 134A, 1234 ZEE, 410A CO2, we have done all of those. Very interesting now for you who are maybe looking into, oh, which fluid is better? Should I, from here, not only think about the physics, can this tell me something about which fluid is better? And here, certainly 32 is far better than 134A, 410A, and so on. Where would be ammonia here? Which we haven't done because that is very difficult in this type of facility, but we plan to do that. Ammonia would be somewhere here. For various reasons, because of thermophysical properties of the fluid. When you go with the different mass fluxes, if you go only 50% increase the mass flux from 100 to 150 kilograms per meter squared in second, suddenly you can have a heat transfer coefficient dramatically higher. Yes, but there is no free lunch. We need to pay something for that, and that's a pressure drop. And that pressure drop will come as a price in the COP when we design the system. So we need to be aware of these issues. If we would look into different heat fluxes, almost no effect of heat flux in a condensation mode, which is great. This is exactly what we know. There is no effect of heat flux in condensation in two-phase mode. But it does have effect here. Because this is here almost like in a, if you remember at least Nussel theory, and that is when heat flux really affects the flow, because thickness of the film on the wall is directly proportional to the heat flux. Thicker the film, lower heat transfer coefficient. This is effect of different saturation temperatures, sorry. And this here is without data yet. We are working on this data too. This is how a model predicts effect of diameter. So you see how we would expect that from 6 millimeter that we have done the experiments now, if we go to 3 or to 1 millimeter in microchannel, heat transfer coefficient will go up for the same mass flux. Now, what happens with the pressure drop? Pressure drop very logically follows this physics that I have just presented with a film on the inner wall and a heat transfer coefficients. Look at this, how beautiful this is. So this is here enthalpy. That means if we would go backwards from liquid, and this here is a pressure drop per meter. That means dPdZ. So for a constant mass flux, we go up, 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 and then the pressure drops start going down, but it goes down also here. And this is the pressure drop in a single phase. This is the moment when the film is being formed. So normal prediction here, like a Blasius equation, would be somewhere here, and this would be Friedel. Very good pressure drop correlation, by the way, for two-phase. So what we are seeing is that, yeah, if you go this way, if you use, because Blasius assumes that you have a vapor only through the dry pipe. What it shows here, that less or more, this is okay, where vapor is, except for this part, here it is okay. But the moment when the film is formed, it doesn't follow that way, because the film existence of the film and increased interaction between shear, between vapor and liquid is increasing the pressure drop. So that is the penalty, or there is a price to pay for 5 times higher heat transfer coefficient than the model would give us, than the conventional models would predict. So we also need to think that pressure drop is going up. In conclusions, I hope this was not too much over your heads, because I wanted to present really interesting, in my mind, extremely interesting insights in the condensation, with not only overall measurements, but complete, with visualizations, with the measurements of the heat transfer for various fluids, and to show you what is really the effect on pressure drop and heat transfer and void fractions. So, everything here I don't need now to repeat. Maybe at the end, you can read it while I'm talking. Maybe at the end what the question would be, and we won't have time for that to talk, is how much does it matter for my condenser? If I use this approach, would my condensers be calculated to be smaller or larger? We have done that, but that will take me another 40 minutes. But typically, depends on what type of other fluid you have, water or air or whatnot, and design of the condenser. This affects more condensers that are air-cooled than condensers that are water-cooled. In water-cooled condensers, the process in that desuperheating region is very short. In air-cooled condensers, especially when you have a low heat transfer coefficient on the air side, this can affect the calculation for between 5 and 10%. So you can, knowing all of this and believing in that being, this is not a church. I mean, these are data. You know, there's a difference. You don't need to believe, to trust. You see that. You can check me. You will get a smaller, like 5 to 10% size of the condenser when you calculate it this way, assuming that all other inputs, like for air side heat transfer coefficients and all of that, is well known and well predicted. With that, I will thank you again and express my deepest apologies for being late for the presentation when I was supposed to be here, and also my thanks for letting me talk before my schedule. Thank you.